Okay, welcome back. Let's talk about the delta shifts that you see in the spectrum. All right, so as I mentioned in the earlier videos, based on the functional groups that you have specific positions in your NMR spectrum where you observe a signal. And paying attention to the ppm values where your signals appear is a good starting point to try to figure out what kind of molecule you're dealing with. All right, and so here I have a representative sample, 8 representative sample of functional groups that we typically observe in the spectrum. So we're going to start with the carboxylic acid. Now, the carboxylic acid is interesting because you do have a hydrogen, which you can observe by proton NMR, and the hydrogen is directly bound to a highly electronegative element, oxygen in this case. So you do have an inductive effect that withdraws electron density away from the hydrogen, and that allows the hydrogen to be, located, at least its signal locates itself downfield in the spectrum. But in addition to the inductive effect, which is just the electronegativity difference, you also have a resonance effect, because if you look at your typical carboxylic acid structure, well, you do have an oxygen with lone pairs next to a multiple bond, so this can resonate or give you a resonance structure. I gotta be careful, how I refer to these things. Um, this can give you the following resonance structure, and what you see right now is that the hydrogen is now bound to an oxygen that bears a positive charge. So not only is oxygen electronegative and withdrawing electron density, but now with that positive charge due to the resonance effect, you have even more of an incentive to withdraw electron density from the hydrogen. So that will make this hydrogen appear even farther downfield in the spectrum. But in addition to that, you have a magnetic effect that plays a role. And the magnetic effect has to do with how the electrons are moving about in your molecule. So if we draw the molecule in the following way, so this is actually the alkene, you know, having the pi bond on the plane of the board. But so the thing is bound to well, it's not really an alkene, right? It's a carboxylic acid. The elements bound to the double bond are going out of the page or into the page. Okay, and this is typically how we avoid drawing, your double bonds. But you'll see in a second why this happens, or why I'm drawing it that way. So consider the pi bond, which is now on the plane of the board as drawn. What happens is that the electrons are going to be moving about the double bond in a circular fashion. Now, if you place this in a magnet, right? So now you have a magnetic field associated with it. Remember that the protons are going to be aligning in the direction of the magnetic field, and because the electrons have an opposite charge of the protons, you're going to have the electrons going in the opposite direction. They're going to be opposing the magnetic field of the magnet. So what happens is that the electrons that are in the pi bond, which are free to move in the pi bond, they have to rotate in such a way that via the right hand rule. And in case you haven't heard of the right hand rule, what you do is using your right hand, and you basically have to follow with your index finger and perhaps your middle fingers as well, the direction of flow right here. So notice how I've drawn the movement of the electrons here going counterclockwise. If you follow that direction with your hand and see what happens to the thumb, like where's the thumb pointing when you have your index finger following this direction of rotation, you'll see that your thumb points towards you. And so what that basically does, this right hand rule, it tells you that the magnetic field of the electrons are going to be pointing away towards you, exactly opposite to the magnetic field of the magnet. And this has to happen every single time when we're doing this analysis, because the electrons have opposite charge than the protons. So they do the opposite of what the protons would do. The protons align with the magnet, the electrons go exactly opposite with the magnetic field, just because of the charge difference. So notice right here that you have the magnetic field of the electron going, pretty much towards a direction opposite of the magnet, but it kind of comes around. So you got to think of this as pretty much being a magnet. The magnet starts at the North Pole, and ends at the south pole. You always have this circular motion for the magnetic field. All right, so now if you start paying attention to what's outside, so if you look at this thing here, the hydrogen is bound to the oxygen, and I'm using the resonance formula right here to give you a much better connotation with what's happening. Well, what happens now is that the magnetic field, by the time you reach the proton, right? So that magnetic field of the electron, by the time you reach the proton, it actually lines up perfectly with the position of the magnetic field of the magnet. And because it's lining up, that means that you have removed that extra burden, to input energy. So this is a means for you decreasing the energy that it will take you to excite the proton from the ground state up to the excited state. And so if you take all of this together, the fact that this hydrogen has the inductive effect, the resonance effect, and the magnetic effect, all removing electron density. Oh, and here's a top view of the molecule, right? So this is how it goes, right? So the magnetic field is going towards the left in this diagram. The electrons have to move about in the pi bond in such a way that um, the resulting magnetic field goes opposite to this thing, right? And then it goes back around. Okay, so the hydrogens basically line up with the magnetic field itself, decreasing the electron density. And this is what I was telling you about, right? So the North Pole goes to the South Pole. This is how magnets work, which kind of reminds me of that meme, magnets, how do they work? Well, this is how they work. All right, so altogether, what this means for the position of the carboxylic acid protons is that they are going to show up very much downfield, and they tend to show up around the 12-14 ppm region. And on top of that, because these are acidic protons, they tend to show up as broad peaks. We'll see that a little bit later when we start looking at spectra. But for now, let's keep an eye out on the position 12 to 14 ppm. That's indicative of having a carboxylic acid proton. Okay, now for the aldehydes, it's a similar story. Now the aldehydes, um, you have an inductive effect going for it because the CH bond of the aldehyde is on a carbon that has oxygen, so the oxygen is withdrawing electron density. There is a lesser resonance effect. It's not as good as the one for the carboxylic acid, because if you draw a resonance for your aldehyde, you're going to end up with electron deficient carbon, basically carbocation. You could say that, okay, well, that positive charge on the carbon will allow you to withdraw electron density away from the hydrogen, but this is not as good a resonance structure as the one that we created before with the carboxylic acid. So the effect is going to be a little bit less um, than before. But you still have a magnetic field because of that pi bond, and it works the same way. The electrons have to move about in such a way that the magnetic field they create first opposes the magnetic field of the magnet, and then they go around to reach the south pole of the quote unquote electronic magnet. And by the time they reach the proton of the aldehyde, well, that kind of lines up a little bit better with the magnetic field of the magnet. So what you end up seeing is that there is an inductive and magnetic field that is perhaps um, the more important aspects of what's happening with the aldehyde. Uh, and the resonance effect is a much lesser contributor. So what you end up seeing with the aldehydes, and once again, here's the top view of what's happening, right? So the magnetic field of electrons opposes initially the magnetic field um, of the magnet. And by the way, when I say that it opposes it, I'm talking about initially to what's happening here around the bond, because this is the initial point of the magnetic field from the pi bond out and then back around, to the back side of the pi bond. So what ends up happening with aldehydes is because they do have the magnetic effect withdrawing electron density, and you have the inductive effect withdrawing electron density, and to a much lesser extent the resonance effect, you still see peaks downfield. Not as far downfield as the carboxylic acids, but downfield nonetheless. And these peaks in particular are very indicative of those two functional groups, because very few things ever show up um, that far downfield in the spectrum of a molecule. So yeah, you could use that as indications that you do have an aldehyde and a carboxylic acid in your molecule. Now, the aromatic peaks have an interesting situation for them, because each one of the carbon hydrogen bonds that you have here are to an sp2 carbon, and the sp2 carbons are much better at removing or withdrawing electron density away from the hydrogens because they are more acidic. They have a lot more S content, 33% versus 25% of an sp3 hybridized carbon. So that hybridization effect kind of allows you to withdraw electron density a little bit better than an sp3 carbon. Now, in addition to that, you do have a magnetic effect. So this is not a resonance effect, this is a magnetic effect. Now, if you consider the benzene molecule drawn in this fashion, so notice that this half side of the benzene molecule is pointing in our direction. The other half side is going to be pointing towards the inside of the screen. And then the CH bonds are on the plane of the board. What happens is that if you have a magnetic field going from the bottom up in this molecule, the electrons are going to move about in the aromatic system in such a way that they first oppose the magnetic field of the magnet. So they're going to have to be going down in direction. And so notice right here that as this starts, you have this opposing effect for the electron magnetic field, and then this goes around, to basically go from north pole to south pole of the electronic magnetic field. But by the time the magnetic field of the electron reaches the proton, you have basically lined up with the magnetic field of the magnet. So in doing this, you have made it easier for the aromatic protons to resonate and be excited. So it will require less energy to excite them, but not as much as the lessening effect is for the carboxylic acids or the aldehydes, because you don't have highly electronegative elements present. So induction effect is really not present here. The resonance effect is really not present here, at least not to an extent that will make it easier for you to withdraw electron density away from hydrogen. So it's really all down to the magnetic effect and the hybridization effect. All right, so the end result is that you still have this peak showing up downfield, but not as far downfield as the aldehydes and the carboxylic acids as a result of the lack of inductive effect and resonance effect. All right, so then that brings us to the alkenes. Not to be confused with aromatics, because aromatics have, that benzene structure, associated with them. This is just a molecule that only contains one double bond or so. All right, so once more, you still have the sp2 carbons in association to your spectrum. So if you do have a hydrogen bound to the alkene double bond, then you got yourself an sp2 hybridized carbon. And that's going to be draw electron density away from your molecule. Now, because there's a double bond present, the same thing that we saw with the carboxylic acids and the aldehydes applies here. The electrons are going to move about in that pi bond to initially produce a magnetic field that opposes the magnetic field of the magnet. But then, as the magnetic field goes around to reach its south pole, by the time you get to the hydrogens of those alkenes, you will start lining up somewhat with the magnetic field of the magnet. Maybe not like to a great extent, but to some degree. So you can kind of see it right here, right? So you have a little bit of lining up happening for the alkenes. It's not perfect. It's not exactly, lining up to be parallel to the magnetic field of the magnet, but it is better than, the situation of, of the electrons themselves as they rotate, opposing the magnetic field of the magnet. So the end result is that you do have some downfield shift, but it's not as dramatic as the carboxylic acids, the aldehydes, or even the aromatics. So they fall between 5 and 6 ppm compared to the aromatics that tend to fall between 7 and 8 ppm in the spectrum. All right, now for the alcohols and the amines, what you will see is that you have an inductive effect because the hydrogens are bound to highly electronegative elements. But there is no double bonds present in here, so resonance effects are not really a thing. And because of that, all you really have here is just the inductive effect helping you out to withdraw electron density away from these hydrogens. So the alcohols and the amines, by the way, they are a little bit fluctuational in the spectrum because where they appear depends fully on the concentration of the sample, the solvent that you're using, the temperature of the sample. So a lot of conditions kind of affect where it shows up, but generally speaking, for not super duper concentrated samples, they tend to appear around 3 to 4 ppm. And the amines tend to fall a little bit less, a little bit higher upfield in the spectrum because nitrogen is not as electronegative as oxygen. All right, and then the alkanes don't have anything in regards to, withdrawing electron density away from the hydrogen. You don't have inductive effect because there's no electronegative elements present, at least not in this example. There is no double bonds or triple bonds, so you don't have a resonance effect. And there is no magnetic effect because you don't have those multiple bonds present. So this tends to show up really upfield, between 0 and 2 ppm. Now that brings us to the alkynes. The alkynes are kind of interesting molecules because on the one hand, you have carbons that are sp hybridized, so they have the most s content and they're the most acidic, withdrawing the most electron density away from hydrogen, just from the point of view of hybridization. But when you consider what's happening magnetically speaking, well, the story is a little bit different. So let's take notice of the position of the alkyne, right? So if we have a magnetic field that goes in the following direction, then the pi bonds, now because it's a triple bond, this is not going to be rotating, the way we had it before, going from one p orbital to another, but rather is going to be going from one p orbital to the other within the same element. So you actually have a rotation that is a little bit different. So this goes in and out. The rotation is in and out. And the rotation has to happen so that the magnetic field, the initial magnetic field of the electrons, opposes the magnetic field of the magnet. So when this takes place, the magnetic field here has to be going towards the right to oppose the magnetic field of the magnet. But as you probably have noticed, the proton is exactly located on the right side of this molecule. So what ends up happening is that because the electronic magnetic field opposes that of the magnet, and the hydrogen happens to be in that location, you have a lot of, I guess you could call it disturbance. So it makes it harder on this proton to be absorbed. So even though we saw that for the alkenes we were showing up at about 5, 6, 7 ppm, the alkynes do not have that feature because the rotation is not exactly the same as the alkenes. The rotation is between the pi orbitals of the same element. So we have a perpendicular picture, if you will, associated with this. So the alkynes actually show up uh, higher upfield than your double bond, counterpart. So 2 to 3 ppm. And sometimes this kind of like trips people over, like they don't understand why this is happening. And the reason why is because they're not considering the magnetic circumstance of the molecule. But with all this being said, we're now going to start utilizing these values to figure out what type of functional groups we have. And then by looking at the shape of the peaks, we're going to be able to deduce what is bound next door to those protons that we're investigating. And we'll utilize the entire information to ultimately come up with a full structural feature for the entire molecule. So I highly recommend that you memorize these general regions where these functional groups appear. It's going to help you out immensely in figuring out what you have in your molecule. Okay, um, so definitely the magnetic field wins in this situation, right? So the hybridization is kind of doing the opposite. Magnetic field is doing also the opposite, but the magnetic field is way more drastic than the hybridization effect. All right, so in the next video, I'm going to start showing you how these chemical shifts, show up and how we uh, can utilize the functional groups to figure out which peaks correspond to what, in addition to the magnitude of the peak and a few other attributes. So I'll see you in the next video.